somewhere. Well, we know that all the TIs generate S. We don't know, the LIs are all sum of G, we don't know what they generate together. Somehow we want a G space. Sorry, we know that all the LIs do generate G, but we need a G space on which all the TI act, and we know to generate S. This is the thing. Then somehow we will know that all the LIs here that we generate G, or then we relate it. So I look at a function space. This is the idea. Just first, we make the remark that maybe phi0 of S is a risk closure. If you want to make sense of it, think about S, or the image of S as the image of the measure. This is Z closure, Z support. More scientific way to relate to this, because the map is only defined at last. So I'm looking at the Zariski support of this set, and I claim that this is gamma invariant, or rho gamma invariant, or alpha. Rho gamma invariant as phi0s, or phi0 as a Z dense image. This is the remark. The image gamma acts on that measure S, and by rho it acts on the image measure, which is M measure on G. Take the Zariski support of this measure. This is, of course, also stabilized by rho of gamma, but it's an algebraic subset, so it's stabilized by the Zariski closure of gamma, which is the full G. So a G act by the related G action that we consider here is the left translation of G on itself. This means that the phi0 is G dense in G. And now we consider the map, which maybe we should call phi0 star from here to, okay, so what is this? G is an affine variety, and this is the space of polynomials, k-valued polynomials over G. And composing these with phi0, I'm getting measurable maps from S to K. So this is like the usual space of functions defined up to measure 0. 0 here means that I don't have any assumption on integrability or boundness or anything. This is just measurable classes up to null set of measurable maps to that field. This is classes up to null set of functions. Okay. From that measured space, S. And of course, this phi0 star has similar equivariant properties as phi0 itself had. Phi0 star again is just a composition of a polynomial here with phi0. Now, since phi0 is Zariski dense, this is why I made this remark. Phi0 star, what can you tell me about it? Is injective. I'm looking at space of polynomials, right? So So if I have two different polynomials, if I have a non-zero polynomial, it will give me a map here, but it will not be zero almost everywhere. Because this means that the non-zero set of this polynomial is of a null measure. Okay. So this is an injective between these two spaces. So what I'm doing now is identifying the right-hand side space with its image. Identify KG with sub-algebra. Oh, this is the K algebra, right? Okay. Okay. Now consider the action of that guy. Gamma acts on the left on S, the TIs do act on the right on S, and of course by composition they map on function spaces, and this algebra, this subalgebra is TI invariant for all I, hence it is invariant under the group generated by those, which is everything. So why is it invariant again? TI act on that thing, and it acts on this by Li, or Li acts on this guy on the right, and it is compatible with this map. So this equivariance means that the image here is TI invariant. By equivariance, by delta I equivariance. So we get that the image is S invariant. In particular, S acts on the image which we identify by KG. So of course, each TI acts on that thing via theta I, but we know that the group generated by all these images must be S. Finally. So we are heading there, right? Okay. I don't. Okay. Okay. What can I say? Now, all the Li actions on KG commute with the maybe I should say, forget this line. This gives a map from S, which is the group generated by TIs, to L, which is the group generated by the Lis, which we observe to be G. And I think we are there. So we get an action of S on G by translations. In particular, we got homomorphism from S to L, and now there is nothing else. I'll leave it to you to check that S to G extends just look at the image of the orbit of that thing. And we are done.
And is it the phi zero after conjugation?
Eventually, yes, you get that it is phi 0. Up to it is phi 0 on the nose, eventually. But now we don't care. So the structure of the proof went, we took S, we tried to represent it as good as we can in some coset space of G. We had some coset space, which still we need to show its non-triviality, G mod H0. We show that H0 eventually is trivial in the sense that it is the identity. And then we got a map from S to G, which, well, this, what we want, this is not yet homomorphism, this is just a measurable map defined after null set with some equivalence properties, but we had so many equivalence properties that we could promote them to be homomorphism.
So let me just say one thing, that's why I hesitated when you asked how
Yes.
you happy. Because suppose you take a representative phi 0 that, let's say phi 0 of the unit element is mapped to the unit element, okay?
Yes.
And but then just by equivariance, you immediately get that theta I of some element t in ti is the same as phi 0 of t. So what I'm saying is,
Yes,
why do you go to the algebra of regular functions to do this? Why
Okay,
can't you
but
just
this
directly-
we discussed this last time. Yes, in principle. Okay, the way Ti is measure 0 in S.
So is it just for this?
So
reason?
I think that the way we conclude here using function spaces, I think it's the neatest way that I could think of concluding. You should agree that it is neat. I don't think it's the only one. Once we are here,
Okay.
I think, yes, if you don't argue about the identity element here, which puts you in the problem of Ti embedded here as measure 0, but you're arguing for some generic point, you will be able to come with an argument. I have no doubt. But this just does it for you. Okay, so again, some kind of a trick or a miracle that you are using, but just save time to do it this way. But I agree with your thought. So again, so this everything collapses now. We are left to fulfill the promise to show that H0 is not everything. That is, H0 is everything means that there exists a representation X. Now this is T1 times gamma. Gamma times T1. Representation X to G mod H. H, not everything. if there exists one, H0 will be, which is a minimal guy in such, will be non-trivial as well. So we need something.
Is this T1?
Oh yes, this is T1. So remember when I said we got started just by T1. A non-trivial representation for T2 was then given with no effort because it was the same one. So I just have to get started. So the next thing I want to present. Oh, okay. So now, so this is a two-stage argument. Two steps. One, show existence of a rep from X. Of course, just there should be some decoration, right? This is T. Now T is T1. I have only this one, and this is G times L, etc. And so X2 not a constant space, but probe G mod H. The probability measures on G mod H. And here you have gamma times T, and here you have G again G times L. L is and this should be directly split to this natural action. So same thing, but instead of taking this algebraic variety, we take this space probability measure, and then show that. Oh, and maybe somewhere I should write it. And H is not G, of course. So that for some, maybe replace H, but still keep it not to be G, can have such amount. X to probe G mod H hits delta measures. If you hit delta measure, you hit a copy of G mod H in it, and then you're done. So I'll present these two steps. The first step is okay. Maybe I should say something. This is maybe I should express a more classical way by Zimmer of doing this. He didn't do exactly these two steps. So Zimmer proved the following. He assumed that the field of definition of G was a local field. Then G was a locally coupled group, so a simple locally coupled group. Then you can take, in such a group, you always have a co-compact algebraic group, non-trivial one, the minimum parabolic. Then he said, okay, we'll take the minimum parabolic here, and maybe I'll do first one for locally compact. Local field. Okay. And elaborate later what to do if the field is not local. Then there exists P inside G algebraic co-compact. And the network. P is the minimum parabolic of G. I want to explain why, if you have G mod P, a compact space, for them, this one is a convex compact space. On which gamma act. Yeah. Now consider X as fix a fundamental domain. F of gamma in S. Now I claim that there exists a gamma map. The fact that there exists, ignore T. Only the fact that there exists a gamma map from S to that compact space is almost a triviality. So S is a gamma times F. And a measure, whatever, nu, just pick a measure in optimal and define then the map to take gamma F to gamma nu is a gamma equivalent map from S to optimal. Okay. Since gamma act with nice orbit to G, I'm forgetting T. Then it is very easy to come up with a gamma equivalent map from S to whatever space on the gamma act. Just take a fundamental domain and map it somewhere, say to a fixed measure nu, and take the orbit maps. Therefore, so this is just one map. The space of maps, maps from S to that space, G mod P, which are gamma equivariant, is non-empty. Now, this itself, L infinity is a dual space, and this itself, this space.
What is the norm?
L infinity norm is this way. So, okay, you have a norm here, and use that norm and essential soup of a point of S to measure distance between two functions.
So which norm do you take? The
On here?
Yeah.
No,
What do you?
I'm fixing a metric compatible with the point. What I'm interested actually is not this as a norm space, but this with some weak star topology. Okay, the claim is this space, maybe I'll write it down, as a compatible, as a natural one, compact, convex, compact topology. So it has a natural weak star topology. Basically, you can embed this in the space of all space of measures, of sign measures on G mod P, which is a dual space, a space of continuous functions, and this is this L-infinity space into that dual space is naturally the dual of some L1 space of this into the square dual of that. So this is, I don't want to write it down. But the thing is that this has a natural topology and of course context structure. Maybe later, I will give you another proof which is simpler, but maybe lengthier. I'm not sure. So just to be sure, I want to start with this one. T acts on S, and so also on this space, S on that space. By T is abelian. In particular,
I guess the reason I was confused was, I mean, the probabilities on G mod P.
yes.
This is if you choose. This has the structure of a complex space.
This is the structure of a complex space.
Therefore, L infinity is somehow the same as L.
Yes, yes.
Okay.
But I do, I use this notation. Yeah, I could just wrote L. I used L infinity actually to indicate the kind of weak star structure that you have on it. I don't want to write it down, but these are standard functional analytic tools that you have here. And T is amenable in fact abelian. Has L infinity S or G mod P gamma invariant has also a T invariant function on it. That's it. That is, we have somewhere, we don't know what and how, but we have a map gamma times T equivariant. Actually, if you think about it, it will be gamma equivariant and T invariant. There is no action of T here, a priori. There will be a function which is T invariant and gamma equivariant. But I'm fine with that. So, the L that is we see here, actually the L will be triggered. Oh, and now, okay. I mean, I hope to have time and to present in a few minutes another proof of that same fact that works also over non-local fields, and it is actually simpler, but let me now proceed as Zimmer would present this and saying the following, something that I did not prove. Later on I will prove, I will give you the argument for two. But now another argument, concluding argument, a la Zimmer. The space of orbits in probe G mod P is smooth, or the action of the G action. Now I'm talking about G orbits, and you have orbits are locally closed in this G action or the space of measures on this G variety is locally closed, and hence the image, the sensor image of S is supported on one orbit. Essentially, the image is supported on one orbit. Some G mod H. And okay. And then you can conclude, instead of this, let me now give you number 2 here. I'll give you a complete argument for number 2. Instead of proving, which I didn't, this smoothness. Okay, so there is smoothness here, and also now I have to argue that this H stabilizer of a measure is algebraic, or algebraic up to some compact noise, which is something that I need to talk about. So I am not going there. This is just a reminder. Now I want to give you step 2 here. So I want to explain why, if I do know to have such a thing, P being the parabolic, then I could find, then maybe upon replacing H, I can actually find something that goes to delta measures. Is it clear where I'm going? I'm trying not to rely on that one. Which I haven't proved. I want to give you a complete proof. So, okay, so 2. And after doing this, I will come back to 1 and try to get rid of the local compactness assumption. So 2, consider, I'm doing the same thing that I know how to do. Consider the collection of all those edges. All H inside G, such that I can find a map at X. And this is, all those maps are gamma equivariant T invariant. All those things that I guess I should have written it here. And pick a minimal limit. H0 and phi 0 to all G mod H0. Okay, now the trick is to consider the map from X to, okay, I can double it. This is easy, I can do phi 0 times phi 0. But now there is a natural map of taking 2 products and take times nu to mu common nu to mu times nu as a measure on that space. So I'm getting a map with similar invariance properties to this space. And what is special about this space is that typically, in the product space, the stabilizers of points are smaller than H0. Here, in Gmod H0, the stabilizer of points are all conjugates of H0. The stabilizer of a point in this double space, a generic stabilizer, it's an intersection of two conjugations of H0, right? Which typically decrease the dimension of H0, and by this I will eventually get contradiction to this minimality. Okay, I need to make an argument, but maybe, so this map is x goes to, I don't know, mu sub x squared. So now I'm considering U to be a certain subset of this doublet space. It will be all the GH, G prime H, such that G inverse G prime is not in N. Okay, what is N? Set N to be a normalizer in G of H0. Okay, where am I? We assumed one. We assumed that we have some H. I promise to come up with another H. The other H will not be H0 that I just found. The other H that will be, we will find in 2 will be N. Okay, the normalizer of H0. Just observe, H0 is not G itself. H was smaller than G by the assumption of 1. H is smaller than G. H0 was minimal such. Certainly smaller than G. And N is its normalizer. So certainly not G itself. Yes. So G is simple in our setting. Okay. No, there is something to explain. G is simple, so when I said that N is the normalizer, I still have to convince you why H0 cannot be a point, the identity point. So let me say this, if G was a point, then I would have mapped X, actually X mod T, to probability measures on G itself. But probability measures on G itself in a gamma covariant way. But I claim that G itself has a G invariant metric on it. So this is a metric space, and also probability measures, and this G invariant metric space, also there is a natural probability, if I'm looking on the probability measures on a metric space, there is a natural invariant metric on that one, and eventually I'm getting a map from X mod T to a metric space, which is gamma invariant, contradicting metric velocity. Or maybe I should try. Should I write down now? Okay. I should write down before considering this set. Remark. H0 is smaller than H, smaller not equal G. We claim H0 also is not the identity. Otherwise, X mod T to hold G is a gamma map into a metric space, a space with invariant, with G in that metric, and constant by metric equality. Check that G has no gamma invariant measurement.
Probability measure.
Gamma invariant probability measure. The action of G on itself is dissipative. It's take everything to infinity. If you have a probability measure which is invariant, you must have quantum recurrence. You must get to the same place over and over again, and this cannot happen. So, putting these all together, we get conclude that N is not origin by simplicity. Okay, so this will be that edge over here. This is my claim. Okay, only now, sorry for this confusion, only now I'm coming to consider this. This here. What is this U actually? U is a we claim that U is an open-ended set. In so this is in G mod H0. This is my V. Is it clear this is a risky open condition? Maybe I'll explain this. So take the product map, or take the G prime goes to G prime inverse G. Take this map. Take N in here. This is a closed. Closed set which is not everything. Take its pre-image. Take pi inverse n. And I claim that pi inverse n, so pi inverse n is a closed thing here. These are the pairs such that the differences is in n. And now project to a G mod H, the natural map from G here. This is an open map. The map from G to G mod H0, the map from a group to the cosset space is always an open map. And the complement of n, so U is the projection of the complement of that thing.
So, should G inverse G prime be not in N?
Not in N, thank you. Yes, and this is the generic condition. Sorry from that. I mean, being in N is some algebraic condition. Not being in N is some open and dense condition. Of course, by the way, N is a closed set, so this is not only this is open and dense. Well, G is connected. This is a connected variety. Every open subset is dense. This is without saying anything. So it is so we're proving 2.
And here we want to write pi pre-image of the complement.
Pre-image of the complement, yes. Here and elsewhere. Okay. So now look at x in x such that mu x square of u as positive measure. So again, I just erase that. So you have the map from x to measures on G mod H, and then G mod H and G mod H. X goes to mu x squared. This is the measures I'm getting, and they may or may not charge positively this big set Q.
And the x goes to mu x. This was
This is
now
the x goes to mu x. This is that mass. Oh, sorry, that's minimal.
for h now.
This is the one for H naught. And I'm considering this double. This is the only thing I have. So assume this is the case. And now
What is the case?
assume this is not clear. Well, yeah, I should.
You mean positive measure?
Assume this is not empty. Okay. So
That is
I
only-
claim it is empty. This is clear. This set. I said.
I would have said measure 0 because it's the map x to mu x or something.
So this is a subset of x indeed. So so it is up to null sets. So the claim is that x never charges this thing. And why? Let me explain. If it does charge, then okay, now I want to restrict again to one orbit. If not, by ergodicity of gamma on x mod t, everything is defined modulo t. It has measure 1. Or full measure. Or everything. And we get a map from x to measures on u. So we have a map from I can normalize things. Normalize to get a map from x to measures on u. U is a variety. It's not G-homogeneous space. It is a G variety. It's a G invariant subset, of course. I did say it, but if you multiply by G here and there. So this is a G invariant variety, and the claim is that if I do have a map from X to any variety, I can somehow disintegrate it to have a map to a homogeneous space in it. So somehow I don't want to say the words ergodic decomposition, which actually comes to mind here. I want to consider the ergodic components here and pick one. I don't want to do it because later on I don't want to assume that my field is compact. I want an argument which is stable also. But the thing is that, well, you have U, and you have a nice map, U to U mod G, and for each measure here, and each element in X gives me a measure here, I can push it to a measure here on this space on which I have no action, and they all will have the same image periodicity. So all the data is by this integration over the fibers. So I'm having measures well defined up to null sets over the fibers. And the fibers are just the G orbits. So I can just take a generic one generic orbit on which everything is defined for almost every X. Okay, so this I don't want to write down this argument in the complete details, but I just want to say if you prefer, you can use the term disintegration here. By disintegration, argument.
It's use words.
Find them up, not just finish writing them down, find them up from X to G mod, well, one orbit in probability measure, sorry, of one orbit in U, contradicting minimality of X0. Ask or answer, then I explain.
It's just, I think this is a bad notion. You have to call it disintegration argument. Because it's not the disintegration of measure that you are applying.
Yes, yes.
Then I misunderstood it.
Okay. So, yeah.
I thought, well, okay, no,
Okay,
repeat.
so,
I thought
I will repeat. Somehow I don't want to write down everything explicitly. For every X, I'm having a measure here, a measure on U. Each measure here, actually this space is, so X goes to something Ux. I'll use this term, but I rarely use it. And it is pushed here to some measure nu. Actually does not depend on X, periodicity. Okay? This integration describes for me the space of all measures with the same things like that. Basically it says this is the same as maps from U mod G to measures on fibers. This integration says that every measure here, fixing X, is described completely by a family of measures supported on fibers of this map. That is orbits. So from every X, I'm getting a function from these two measures defined over fibers here. And I just, so actually I'm having a map from X times this guy, two measures supported on fibers, and I'm using a Forbini argument. I'm fixing a point here and getting a well-defined, almost well-defined map from X, two fibers, two measures on that fiber. So we that's me here to interchange the almost everywhere on X and almost everywhere.
yes, okay. You mean to argue that each Ux is supported on one orbit? This is just the ergodicity of the gamma H, but you want together to a map from X to probability measures on one over.
Yeah.
Okay.
So again, I'm using this, I'm thinking of this integration as mapped from this space times that space to a certain space of measures on fibers, and then it is defined, well defined for almost every pair here. I mean, to begin with, it's for almost every X, it is well defined for almost every such guy. Fubini tells me that I can interchange this almost everywhere definedness, and this is what I do. And then I pick a point here for which it is defined for almost every X. Do you know this integration of measures? Excellent. I know that you. But okay, so just and the orbits of U was designed such that the stabilizer of points are smaller than H0, right? What is the stabilizer of the point given by G, G prime? It's the conjugation of H by G intersected by the conjugation which is
H is H.
these are H0s, which is as small as H0, right? It is minimal. And we intersect it with the conjugation of H0 by G prime. Is it the same thing or something else? If it's not, okay, if it's something else, we increase the dimension, we contradict inequality here. So we conclude, so we prove that, we put that there. It has measure 0. Sorry, I have no more time, I guess. What is the time? Okay, let me finish this. And I guess I will not give you one now. I mean, I will not give you the other version of one that I wanted, but let me finish this two. Okay, I'm almost there. Almost there.
Well, some don't need to finish it now.
But I do want to finish it.
No, this
That
is
first. To finish this argument.
This
I don't care about non-local context. Yes, about this.
Okay, but so also for the local field, you can use Zillow's argument.
No, but it's somehow funny. You were happy to present the proof for SL3 as a special example, but you care about the generality of the field here, which is, I think, okay.
Yes, I know. Because this is
I know.
you know. Sorry. Yeah, this is a bit ridiculous. Just a minute. Okay, so in the complement, I also now claim, which we check it together, that we have a well-defined map okay, we have this map G mod H0 to G mod N, of course, and the overlap. So G mod H0, so G mod H0 times G mod H0, so G mod N times G mod N. I want to say the following, sorry. I want to claim that when I push now using this map, and I'm looking at the image of X in here, as delta measures at the image. This is my claim. Now, this is at least what I wrote in this page over there, and now I can explain this, and the class here and let you figure that. I mean, it should be clear. It is not clear to me now. But it's the fact that I'm not hitting you. To focus on read this one. Okay, so for any mu x, take this x, it goes to mu x here. Okay? And actually mu x is supported only on the n orbit. Yeah. Consider mu x here. Let me using my fingers and mouth instead of the chalk here. Consider little x here, the measure mu x here. We know that mu x times mu x doesn't hit u. So almost every pair of points are differ. So g and g prime are differ by an element of n. So they're in the same n orbit. All the elements of mu x. When I mod n, and this is exactly n is acting on the right here. Normalizer of h0. So this is like modding n. Modding n, this mu x collapses into one point. I mean, the support of mu x is collapsing into 1 point, and this point, and the image of the measure would be the delta measure at that point here.
So, what you should, when you're at this point before contradicting reality, this was the end of.
This was the end of showing that you get no measure. Yes, all the measure is supported on the complement of mu. So any point for every little x, I'm getting a measure mu x here.
Just this was part of the proof that this
Yes,
set over
yes,
there is a null
yes,
set.
yes.
Okay.
Which means that for every little x,
Yes.
u gets no measure. So the measure mu x is supported on the complement of, is supported on that thing. The g and g prime are related by an element of n. They are in the same n orbit. N act on g mod h0. And if these are 2 points in the which both are in the support of mu sub x, these 2 points are related by an element n. They are in the same n orbit. I don't want to write it down now. It's too late for that. But I do want to explain because
I'm a bit lost now. So you claim you have
I claim
shown
that-
to us that this has.
yes, I'm looking at the x. I'm looking at mu x.
Yes.
And this is n measure on g mod x0. I'm considering it as a risky support of that one. Okay? So, and I'm claiming that it is some, so n act on the right here. And I'm claiming that the risky support of this is some n orbit, a unique n orbit.
Okay.
Otherwise, or if you wish, I claim that maybe I should express it like that. Here, take g mod h0 times g mod h0 to g mod n times g mod n. Take mu x times mu x here and push it down here. Delta measures are exactly measures which are supported on the diagonal here. A delta measure on a space can be described as a measure which is supported on the diagonal on its double. And the double of the measure is supported on the diagonal. This is what we want to express. And I want to claim that the complement of u actually is mapped to the diagonal here. Yes, I think that, I guess this is is a better way to express this. U is exactly, U is U complement is parametric. I mean, this is by definition. Does that make sense?
Change the definition of U there.
Yeah, it was.
If you attend then not in,
It was not in
It was not. Still is.
then it's U.
And no, this fits with bad definition.
Too many negations. Yes. Okay.
Is that okay with you?
Well, yeah, you see goes to del, but somehow,
You see,
U,
goes
and we showed before that mu is mu x squared has support in UC. Okay. So
exactly. So
support-
mu
I
x,
see.
mu
Okay.
x times mu x has support in here. So its image in here has support in here.
Okay. Now,
And this is some double measure in here, and this is the property. The only double measure that are supported on the diagonal are delta measures. Yeah, I guess
now I
this
understand.
is the better way to say it. End of the course.